In the last video, I talked about the simple linear regression model, and in this video, I'll talk about how we estimate the equation of that simple linear regression model. And it turns out that if we think about how we might do this by eye, that actually mimics the way mathematically that we can use software to estimate the model. So we'll use our home price dataset again. So remember, we have 5 houses with different sale prices and floor sizes. And what I've done here is I've plotted the observations on a scatter plot with sale price on the vertical axis and floor size on the horizontal axis. And we're going to just estimate by eye which line fits the data the best. So I'm going to start with this horizontal line, and it doesn't really look like that line summarizes the relationship in the data very well. We can see that there's a positive linear relationship between floor size and sale price, but that horizontal line does not really summarize that relationship very well. So it looks like we need to tilt the line up so that it's got a positive slope rather than a zero slope. So we'll tilt it up, and we can see we're getting a bit closer to the points now, but I don't think we've gone far enough yet. So let's keep going. So that's starting to look a little better. The line is closer to the points than it was before, but maybe it's not quite there yet. So maybe one more jump. Now that looks pretty good. I would say that line fits the data pretty well. What if we went a little bit further? Maybe we haven't gone far enough yet. Well, now I think we've gone too far. Now we've overshot. And if we keep going, yeah, now it's getting worse. So I think that's pretty good. So here's all the lines plotted on a graph all at once. So those are the dashed lines, and then the solid line is the one that I think fits the data the best, this one. So how could we turn that into a mathematical algorithm that would give us the same answer every time? Because obviously eyeballing this isn't going to be very consistent from one person to another person. We're all going to come up with slightly different answers. So we need a mathematical way that will always give us the same answer, but that's using the same basic principle. Keep moving the line until it fits the data the best in terms of being as close to these points as we can get. So to do that, we're going to revisit one of the ideas from Chapter 1, Statistical Thinking, where we have a population and we're trying to estimate what's going on in that population using a sample. So in this case, the population is represented by the simple linear regression model that we talked about in the last video. Expected value of y given x equals b0 plus b1 times x. b0 is the y-intercept, b1 is the slope. So that's our population model. We have sample data, and we're going to use our sample data to estimate the model. And the notation that we're going to use here is y hat represents the fitted value of y. b0 hat represents the estimated y-intercept. b1 hat represents the estimated slope, and x is the input floor size. So if we can put numbers in here for b0 hat and b1 hat, then we would be able to plug in a particular value of x, say x equals 2, and then evaluate what this comes to, and that would give us a fitted value of sale price, or a predicted value of sale price. So that's the idea here. So the question is, how can we obtain numbers for b0 hat and b1 hat? The way we do that is we find a best fit line, which in statistical terminology is called a least squares line. Because if I had numbers here, a number for b0 hat and a number for b1 hat, this would be the equation of a straight line. And the particular straight line that works here is the best fit line, the least squares line. So how do we do that? Well, mathematically, we're going to minimize the residual sum of squares. So the residual sum of squares, RSS, is the sum over the sample, I equals 1 to n, of EI hat squared. Okay, what is EI hat? Well, EI hat is the residual between the observed value of y and the fitted value of y. And remember, the fitted value of y is given by this equation up here. So we could write this as the residual sum of squares is the sum over the sample, I equals 1 to n, of yi minus b0 hat minus b1 hat times xi. That residual gets squared and summed over the sample. So this is now an optimization problem. We've got a function with two unknowns, b0 hat and b1 hat. We can maximize, sorry, not maximize, that's the opposite of what we want to do. We can minimize this function with respect to b0 hat and b1 hat. So if you have done calculus, you'll know that we can do that using partial derivatives. But if you haven't done calculus, don't worry, because we're going to just use computer software anyway to find b0 hat and b1 hat. Just think about it though as minimizing this function RSS with respect to b0 hat, the estimated intercept, and b1 hat, the estimated slope. So in a picture, what this looks like is we've got y on the vertical axis, sale price, x on the horizontal axis, floor size. We've got our plotted points, that's the 5 points, and then this line now represents the estimated equation, y hat equals b0 hat plus b1 hat times x. Okay, I'm putting in the actual names of the variables in this example. So y is price, house price, x is floor size, and so along the line we would get the fitted values or the predicted values of sale price for a particular floor size. The individual points aren't all the way along the line. So for example, this fourth one, the sale price is a little bit lower than the fitted value, and so the difference between the two is the estimated error or the residual E hat. And so we can write an observed value of price, sale price, as b0 hat plus b1 hat times floor plus that residual E hat. I showed you the computer output in the last video. Let me just show it to you again. So there's a lot of this output that I'm not going to talk about just yet. We'll come to in future videos. But the bit I want to focus on is the 190.318. That's the estimated intercept b0 hat. And then the 40.800, that's the estimated slope b1 hat. So that's our estimated equation there. And what these numbers mean is, let's focus on this one first. If I plug in x equals 0 into this equation, I would have 40.8 times 0, so that would just go away, and I'd be left with y hat equals 190.3. So the 190.3 is what we expect y to be when x equals 0. But that's only practically meaningful if it makes sense, and if we have data close to x equals 0 for it to make sense. So in this case, what would it mean? It would mean a house with a floor size of 0. Well, that doesn't make any sense. And so mathematically, this is a necessary part of the model. It's one of the defining numbers in the model that defines the equation and defines where on the graph the line is. But practically speaking, in this particular context, it doesn't have any practical meaning. So that will often be the case. The y-intercept will often not have any practical meaning, but it is absolutely necessary for the model to work. So keep that in mind when you're asked to interpret the estimated y-intercept. You can only do that if it makes sense in the particular context, and if you've got some data close to x equals 0 to support that particular value and that particular interpretation, neither of which we have in this case. The 40.8 though, so this part of the model, this is the estimated slope, that always makes sense. And what it represents is the expected change in y when we increase x by 1 unit. Okay, and it's important to think about the measurement units here. So what is 1 unit of x in this particular example? Well, x was measured in thousands of square feet. So what the 40.8 means, and remember we've got to think about what y is measured in as well. So we're going to expect the sale price y to increase by $40.8 thousand, in other words $40,800, when the floor size increases by 1 unit, 1,000 square feet. So that's technically what the 40.8 means in this context, but it perhaps might be a little more meaningful to just change the scale here, so it's going to be more applicable to the situation at hand, and it's easier to think about 2 houses that differ by 100 square feet than 2 houses that differ by 1,000 square feet. So if 2 houses differ by 100 square feet, the one that's larger by 100 square feet would on average have a sale price that was higher by $4,080. And where I'm getting that from is the 100 square feet. To get from 1,000 square feet, I'm dividing by 10. So I'm doing the same to the 40,800, dividing by 10 to get the 4,080 here. So that's an important part of interpreting some of the output from a simple linear regression analysis, is you get your table of parameters or coefficients, and you look for the y-intercept, and you look for the slope, and then if it makes sense to interpret the y-intercept, you can. If you can't, then you have to just say it's mathematically necessary for the model, but it doesn't have any practical meaning. If it did have practical meaning, it would be the expected value of y when x equals 0, and then the slope always has meaning, and it's the expected change in y when x increases by 1. So we've talked in this video about how to estimate the equation of the model, and in the next few videos we're going to talk about how to evaluate the fit of the model. So we're going to think about different ways of measuring numerically how well the model fits the data.